Okay. So this is the exercise class, and it's supposed to be easygoing. If you have any question, you can just ask. But for this time, I think I will just revise the material a bit and try to go over the exercise that I asked in class in slower pace. And but later in this class, as I kind of mentioned in the beginning, this class there will be open problems that that we will try to solve. Actually, I have listed a bunch of open problems, and but we will not discuss this yet today. I will kind of wait until there are more. I'm ready to present it more than this, basically. So, right. So this week we have seen the definition of conductance of a cut, and but which is just the number of edges crossing a cut over the volume, right? By the way, what would you define the conductance of a graph or of a cut if a graph is weighted? It's not just unweighted graph. How would you define it? Like, what is the thing that should make sense?
Using volume as a degree, we'll use weight by 2 maybe for each vertex.
You use weighted degree instead of unweighted degree. Yeah. And what about this?
That's just some of the...
Right. So, yeah. So when the graph is a weighted graph, then we can define the conductance like the weight. So let's say that. So let me say that given the weight function, right? We define the weight of a subset to be just as for any subset. It's just a sum of the weight in a subset, and so conductance of a cut is now summing over all weight crossing the cut over the volume. I will still write volume, but now the volume is defined to be I will still write degree as well, but degree is really the weighted degree. That is, if this is like if this is 10, 1, 3, 1, then the degree of this is 15. Sorry?
Is it not weight by 2?
Weight by 2? What do you mean? I don't understand.
I mean half of the weight.
No. I will just like sum them up. Yeah. So this is the conductance of weighted graph. And conductance of a graph is just the same thing, just minimizing overall conductance of a cut, right? So that is a weighted graph, and let's kind of try to see a bit why it makes sense to define it this way. This is because we have seen that like if a graph is a path, then it has very bad conductance, right? If the conductance is something like 1/n, but if you instead look at the path, but now you define the path such that the weight here is n minus 1. Oh, this is still bad actually. I think you need to define it like, actually, let's try. Can you tell me how would you assign the weight into the path so that the conductance is good, is constant?
Just power 2 to the power 2.
Good. So maybe you can put this 1, and then like this is 2, but like this is 4 now, and like the more you come into the middle, you grow the weight exponentially, right? And why is this good? Because you can see that even if you cut in the middle, the sum of the weight here is kind of still proportion to, like the volume that you cut is still proportion to the edge that you cut, right? Okay. All right, and then chuk. Exercise. Where is exercise? Actually, let's do this. The thing that I left out yesterday about this question. So anyone can answer this. So just to remind you, we have defined like a more general notion of expansion to be the expansion, where now like instead of the expansion of like the expansion is defined to be kind of you replace the volume with a function d here, all right? And what if I set d to be just all 1, that is each node got like a demand of 1. Can you give me the graph where the expansion with respect to this demand d unit is high, but the diameter is big? So let's just try.
I cast a circle and connect the vertices with distance less than square root of that. Maybe it can get it quite.
Let's wait a bit so that everyone can try. I will just give you like 5 minutes. Yeah. By the way, is the question clear? Really feel free to ask questions. This is like a very safe place to just ask things. Oh, I define D to be like unit. So every node have demand of 1 here.
But it would be the same as conductance if you define it as the degree.
Right, it is not the same as conductance.
So every vertex just has value 1.
Yeah. Okay, so my first question is maybe, is this quantity bounded by 1? And the answer is not really, actually, right? For example, if you look at a complete graph, how big is this quantity? It's going to be something like at least n, actually, right? Like O of n. Because if you look at any cut S, then the number of edges that go out of the set is something like S times this. But the minimum of, and what is D of S? This is just the size of the set S. So this thing is like it's basically around something like O of n. So that's the first thing to note. Like this quantity can be actually at least n, and if you think of weighted graph, it can be infinite, really, right? You just put the weight on an edge. And now, okay, so you can make this quantity as large as you want, really. And what if I just look at this graph where the graph that you have seen before is just a path. And what if I put the weight to be infinite on every, or maybe you also can think of, instead of putting weight, I put a lot of edges here. It's still unweighted graph, but now I can put the edge as much as I want, and this quantity will be as large as I want. But the diameter of this graph is still going to be very large, right? So that is the example of this exercise.
Is that possible for polygonal graphs?
Yeah, is it possible to make the graph, you mean simple, not there is no parallel edges? Yeah, so what do you think? Can we do it? So let's see. What if I just, instead of doing this, I kind of make a layer. Let's say layer of size n, and then I make a complete graph, complete bipartite graph between them. So there is no parallel edges. All right. Is this good enough, actually? So the number of edges here is n squared, and yeah, good. The number of edges here is n squared, and so let's say that there are n nodes here, and there are n layers. So when you cut it here, the number of edges is n squared, and the number of nodes here is also n squared. So this is big, like still constant, but the diameter of a graph is still n. And okay, like we kind of need to convince ourselves that this is a sparsest cut. This is the cut that actually there is no other cut that has that gives smaller expansion, but yeah, intuitively it is the case, right? All right. So the next exercise, let's look at this one. So this exercise is about there is a graph. It's like it's a way to think about like what can we measure, how well connected some subset in the graph is, right? So maybe the graph is very like it's not very well connected. It's even disconnected. There are a bunch of connected components, but maybe there are some set of us inside the graph that is well connected. So thing like this, like maybe this is a clique together with a path. Yeah. So if you just cut this thing, you disconnect a bunch of things. But so this looks like a sparse cut. So this graph is not very well connected, but you should still be able to say that inside this clique, this is still well connected. So so now can we say something like this in general? That is, given a graph and some terminal set, how would we measure how well connected this set is? All right, and we can just try to do that. For example, like basically this notion of the expansion allow us to measure that thing. So how? Basically, let's say that T is a subset of terminal, just some subset of the vertices in the graph. And we just set the demand to be maybe degree for everyone in the terminal set. And everyone else, we don't care. Just set it to be 0, right? Then you can see that there must exist some connected graph that the demand, like the expansion with respect to this terminal, with respect to this demand, is big, but the conductance of a graph itself is very small. And the example is just something like this that I just showed, right? So can you, let me give you some other example that is kind of more non-trivial. So suppose that I start with a graph which is an expander. Let me say that G0 is an expander. So it has high conductance. So maybe think of it as some random graph that we discussed yesterday. A random graph is an expander. So yeah, they are like a sparse but very well connected somehow. All right. And let me try to construct another graph, G from G0. So this is G0, which is such that the conductance is big. But now for each edge in G0, let's say that I subdivide an edge into a path, into a long path. Okay, I just do this for every edge, and then I get G. Is it clear to you that the conductance of this graph G is going to be small? Why this is like let's say that this is like of length n, then the conductance of G must be at most something like 1 over n. Can you tell me why is that the case?
We just have two S and get a whole chain disconnected.
Right, right. So because you can just define this to be a cut, right? So you can just cut two edges here, and then you disconnect the volume of n, okay? But now, intuitively, you can see that, okay, it's true that this part of a graph is not very well connected, but the purple nodes in the beginning it seems like the connectivity between them is that it doesn't change. You just like change an edge to a path, right? So can you try to prove that? I define the purple node to be the set T. Prove that the conductance, like the expansion with respect to this demand is still good. Yeah. Where demand of U is like a degree. Yeah, just define it like this. Demand of U is a degree if it is in the terminal set, which is a purple node here. Otherwise, it's 0. So let's try to argue that.
What do we have to show?
Yeah, if you have some argument, you can just tell me. Yeah.
What was the question?
Oh, the question is showing that
The connected graph G where
in this graph G that I constructed this way, with this terminal set to be, the terminal set is the purple node, the node from original graph G0. Show that in this graph, this quantity is big. The phi of GD is big.
So we are given that the previous graph has omega of 1.
Yes.
So in that case, according to the definition, the denominator doesn't change, right? Because we are giving 0 to everything else. And the numerator also doesn't change because we are only expanding the edge, not like adding more edges between only these vertices. The degree, like though S doesn't change. With respect to only the purple vertices.
Yeah.
If we are cutting this, any one of this path on that edge, any one of these subdivided paths, then it's equivalent to cutting the edge, and we are only going to cut pure edges.
Exactly. So let me just rephrase what Chaitanya and Aditya just said. So how do we show that this is big? What we want to show is actually that maybe we want to argue somehow that this is related to, like from the, we must somehow use the fact that G0 is an expander, right? So we want to show. Actually, we will try to show that something like this. And how do we show that? That is, what we would try to show is that given any set, any cut in G, given a cut in G, I can construct a set S0 in G0 such that the conductance, the D expansion of this is something like this. If we can show this, then we are done, because we know that this is always big, right? This is big because G0 is a like a constant expander here. Okay. And now what do we do? Like maybe we just say that, okay, let's look at any cut really in G. Maybe like the cut might look like this. Yeah. But yeah, what we try to do is just saying that, okay, define the set. Then naturally we'll just define the set in G0 to be this node, right? To be this node. And yeah. And we can see that the denominator is the same. So this thing, this is just the number of edges. And what is this? This is really kind of, so let me assume for a bit that like maybe right. So, am I correct? I think so. T minus S. So this thing is just this thing, right? But, and this is in G. And first of all, we know that the volume of each node in T are like the same as volume of like the degree of each node in T is the same as the degree of each node in T have the same degree in G and in G0. Yeah. So this is mean. So this is really the same number. Yeah. And what about, and I also claim that the number of edges that cross the cut of S will be at least the number of edges that cross the cut S0. Why is that the case? Like, this needs some like proof, like, but you can see kind of from the picture that So the cut S here can only like cut more thing. Like here, you have more edges, more cut edges here, but at least you must cut through like, so if you, what I mean is that for every edge that you cut in G0 here, S must cut through some edge in this part too, right? So that is why for every edge that S0 cut through, you can get 1 unit of edge that you cut through in G as well. And once we have this, it implies this thing, and we are done. Okay.
How is the dou defined with respect to DE expansion? D function.
How is what defined?
How is the dou?
The partial here?
The cut.
Oh.
Yeah, the cut.
I still define it as in the same way. So it's really just the number of edges crossing the cut.
Okay. So the D is for vertices.
D is for vertices.
The D function.
The D function is only for vertices. Yeah.
So how do we define it for dou is? So it doesn't change is what it is.
Yeah, nothing changed here. The thing that changed is just here compared to the conductance. Yeah.
And how does the dou change when T is added? Terminal.
I don't quite get the question, sorry.
How is the dou partial changed when we only consider some subset of vertices as T?
Oh, I mean, I define. So I define here to be just really. S0 is now S intersects T. So it's like when we define it here, S0 is now a cut in G0. I'm not sure if I answer your question.
The reason is, so in this example where there is the same edge getting cut multiple times with respect to T, but not with respect to,
You would still count it multiple times in it.
Yeah, so So, I mean, this is just a cut in G, right? And it can cut through the path multiple times. And this is a cut in G0. My claim is just that for every time that you cut through some edge, every time that S0 cut through some edge in G0, the cut S must cut through the corresponding path at least once. It can cut more times, but yeah. Okay. All right. So there are some other exercise that we didn't show in class. How about this one? Just to remind you, vertex expansion is just the number of some vertex cut is the number of nodes that you cut compared to the number of vertices that you disconnect from after you deleting uh, the set of node, all right? And here we define vertex expansion to be minimizing overall vertex cut. And now let's try to prove that if the vertex expansion is large, at least 5, then the diameter must be small.
What was the E approximation?
Oh, so something like this is kind of the same as this thing when x is small. So
The rest of the only replace volume by number of vertices.
yeah. So actually, the argument would be very similar to what we did in class. We recall that the key idea that we did in class is that where is it? Here. We show in class that, okay, if the graph is an edge expander, then we look at the ball around any nodes with radius maybe r plus 1. Because it is an edge expander, the volume must grow quickly per each radius, per step. Now, if the graph is a vertex expander, we just don't look at the volume. We look at the number of vertices in the ball, right? So we will be able to show something like the number of nodes inside a ball, starting from S, will be now something like 1 plus 5. So maybe I just write it like this. It's obviously at least the guys in the ball of radius r plus, let me call it this neighbor, the neighbor set of and by neighbor here I mean that if this is a set of nodes x, then neighbor of x is just all nodes that are incident to x. Okay. And we know that the neighbor of this ball will be something like at least 5 fractions of the size of the ball if this is a vertex expander. Yeah, and now it means that the ball actually grow in the number of nodes, kind of geometrically. And then we use the same kind of argument we did in class. You grow ball from S and T, and they kind of grow geometrically at each step from both S and T, and that cannot happen like logarithmic many times. Otherwise, it's going to be too big. So that's why the ball must meet after some logarithmic step, and that's why the distance between any two nodes is going to be small. So note that like this is why like an kind of you can see right if you compare like for conductance, graph with high conductance have low diameter because we kind of compare the number of edges. Like the notion of conductance is about comparing edges, the number of edges and the number of edges in the ratio. For vertex expander as well is the number of nodes compared with the number of nodes that you disconnect. But we saw some example when we saw an example, where is it? Here. That is, here it's just kind of the nature of notion. You compare the number of edges that you cut from the number of nodes that you disconnect. But because of this mismatch, you compare edges with the number of nodes. You cannot really conclude that the graph have small diameter in this case. Yeah. Okay. right. Sorry. So let's just try to do this thing as a last exercise for today. Actually, I forget to ask. So, is there anyone who would like to scribe this note, actually? Oh, you? Okay. Or you have a question? Or you want to scribe it? Okay. Cool. All right. Thanks. Okay. So this problem asks this, right? That is, just to repeat, you have a graph G, which is a vertex expander. And what do you do without any preprocessing on the graph, such that given any set of nodes to be deleted, you want to check if S and T are still